Alright, so this lesson is on enthalpy and change in enthalpy. We'll be learning how to calculate the change in enthalpy. And although you can't actually measure the enthalpy of a substance, what we will be measuring or calculating is the change in enthalpy, which is the heat absorbed or released during the chemical reaction. This change in enthalpy for a reaction we call the heat of reaction. And then we'll show that as this little triangle H, which means delta. We say delta H for the reaction, and if you remember from one of the previous lessons, that little triangle delta means change in. So another type of enthalpy is heat of formation, and what the heat of formation is the energy needed to form 1 mole of a compound from its elements. And one of the things that we have to remember is that delta H of the elements is actually 0. And then these values we can find in a table, or in class most of the time we'll just give you these values. But remember that if it's a pure element and it's in its elemental state, then the delta H for that element is 0. And then the other thing we want to make sure we remember is that heat of formation is always to form 1 mole of a compound, 1 mole only. So this is the equation that we're going to be using to calculate any of the change in enthalpies, whether we're calculating change of enthalpy in reaction, formation, combustion, whichever kind of enthalpy we're going to be calculating, we're going to be using this formula down here. And let's talk about what some of these symbols mean. Of course, we have the change in enthalpy. This funny looking backwards E is a symbol in math that means summation, means we're going to take the sum of. The little n that is pointing to in the blue, that means moles from the balanced equation. And this is always going to be your sum of your delta H's for your products minus your sum of delta H's for your reactants. So it's always going to be products minus reactants, products minus reactants. And so let's just do a couple of calculations so you'll see how it works. Alright, so this is just another example of what I just told you, that if I was going to calculate for heat of combustion, I would use that same formula just like I did for heat of reactions. It's always going to be products minus reactants. Again, remembering if it's an element in its elemental state or its natural state, then that value is going to be 0. And you'll see that in a couple of the calculations we're about to do. Alright, exercise 1, calculate the heat of combustion for this reaction. We've already got our delta H values for the compounds listed, and then I went ahead and gave you the formula that we're going to use. So now it's just a matter of literally plugging in these numbers and doing the math on our calculator. So let's start with products minus reactants, and we're going to sum them. And so we're going to start with the delta H of combustion is going to be equal to, and so my first product that I have is I have 5 moles of CO2. So I'm going to say 5 times the value for CO2, which is a negative 393.0, plus I have 6 moles of water. And so I'm going to do 6 plus my value for water, and not plus, times, which is a negative 285.8. And then I'm going to sum that, and I'm going to subtract from that the total of my reactants. Alright, and I have 1 mole of the C5H12, and so since I just have 1, I just have to put the negative 145.7 and then plus oxygen. But remember, if oxygen is an element, which it is, and it's in its natural state, which it is as O2, it's actually going to be a value of 0. So we're just going to put that 0 down so we know why we didn't put something in its place. So now we just add these up. We plug it in our calculator just like it says here, and when we do that, we should get an answer, hopefully, of a negative 3,534, and then the units that we would use would be kilojoules per mole, and it's because we have kilojoules here. Alright, so that's how you do that one. If you didn't understand exactly what I did, go ahead and stop the video, replay the slide, and make sure you're understanding where I'm getting these numbers. Alright, just in case you had trouble knowing where I got those numbers, I went ahead and labeled them for you, so you can go back and look at that if you didn't understand what we did. So let's go on and do the next one. Alright, so let's do this one. Using the enthalpies of formation, calculate the standard change in enthalpy for this reaction. which is thermite, which is very explosive, by the way, and there's a picture of it there. So the first thing I notice is that I've got two elements in my equation, and so I know that this value is going to be 0, and iron is also going to be 0. So when I go to plug those in, we'll just use a value of 0. So let's calculate our delta H formation of this stuff. So it's, again, products minus reactants. So from the product of aluminum oxide, I have a negative 1676. It's just 1 mole, so I can just leave that out, plus the 0 for iron, just so we know that it's there, and then minus the reactants. So I have the 0 for the aluminum, plus the value for the iron oxide, which is right here, so it's a negative 826. And then when I put that in my calculator, I should get a value of a negative 850 kilojoules per mole. And of course, the fact that that is negative means that this reaction would be exothermic, and clearly it's explosion right here in the picture, and so it is an exothermic reaction. All right, one more calculation, and then we're done. All right, last problem, and it's a little bit trickier. So it says calculate the delta H of formation for C3H8, which is propane, and it wants us to calculate for that value. It's actually not giving it to us, but what it is giving us is it is giving us the value for CO2, and it's giving us the value for water. And of course, we know since oxygen is an element that that value is 0. So it's giving us everything but the C3H8, but it's also giving us the total. So what we have been solving for as far as delta H, it's actually giving us the entire thing. So we're going to set these things up equal to that and then solve for C3H8, which is going to be X. Okay? So we're going to start with the same formula, but we're going to say it's equal to negative 22.19.2 kilojoules. Same thing with our products minus reactants. So let's get our products. We have 3 times the value for CO2 is a negative 393, plus our water, which is 4 times negative 285.8, minus our reactants, which is X, right? We have X, plus, of course, 0 for oxygen. So now we start doing that math, and then it's just going to be a matter of solving for X like we learned how to do way back in Algebra 1. So negative 2219.2 is equal to, and then when we add those up, we get a negative 1179 plus a negative 1143 minus X. And then that works out to be a negative 2219.2 is equal to a negative 2322 minus X. And then, of course, to isolate that, we're going to add 2322 to both sides plus 2322 to both sides. So then that gives us 102.8 is equal to negative X. And, of course, we need to get the negative on the other side, so we divide by a negative 1 on both sides to get that negative over there. So we're left with X is equal to 102.8, which for significant figures, we're going to go ahead and put that, actually we could just go ahead and leave it in 4, because everything up there had 4. And so it's going to be a negative 102.8 kilojoules per mole. And that is our answer. And what we did there is just some simple algebra that hopefully everybody remembers. If you did not understand that, then replay the video in case I went too fast, because I know I tend to do that. If not, move on. And the last slide is, of course, as always, the jokes. And, of course, as always, if you don't want to listen to the jokes, stop the video now. All right, joke time. Here we go. The theme of this is jokes that can be found on Laffy Taffy. Here we go. What has no legs but can do a split? A banana. What room can no one enter? A mushroom. What kind of tree grows in your hand? A palm tree. And then lastly, what is smarter than a talking bird? A spelling bee. All right. See y'all in class.